And again, we've already indicated that h is simply the separation of each of those data points on the x-axis. And that's important to realize that most of these approximation formulas are going to be based on equal spacing of these points. X plus h, x minus h, x plus 2h, x minus 2h, and so forth. So you have to have equally spacing for these particular formulas. So one technique that is available to try to, what we would say, boost the accuracy of the finite difference approximations, are there ways we can use these formulas sort of in a constructive way to improve on that O of h squared accuracy? And there's a technique called Richardson extrapolation that we want to cover. Very, very effective method and can be easily incorporated into software. So we'll just start off with a generic representation of a process where, suppose that we want to approximate some quantity g, and let's suppose that its process or the formula or the approach is given by, you get it by doing this particular approximation g of h, and then you have error associated with that. Just like we did before with taking Taylor series and then stopping after so many terms, and the terms you threw away will go into the e of h there. But let's suppose that that error term e of h is of the form of some constant times h to a p power. So we're representing the error as O of h to the p in general. Okay. So if we were to do a first approximation using this rule, we could say, let h1 be our approximation that we got by applying our rule, g of h1 plus, and then the error would be c times h1 to the p power. And then do the same approximation with a different step size. In other words, we would let h become h2, and the formula would be the same as before, but it's using a different value for the step. So it might be like doing a finite difference approximation with h being 0.01 and then turn around and having it to be 0.005 or something. So it's like using the same rule twice with a different value of h. Okay. So if you took those two expressions and you used the right-hand side for this value of g that we're approximating and eliminate the constant, this would produce what's called the Richardson extrapolation formula, or REF. That a better approximation to g would take on a form like this of the ratio of your two different h's that you chose to the p power, and that would show up in the denominator term, minus 1. And this factor would be multiplied by whatever you got from the second step size minus what you got on the first step size. It is very common to just sort of half the step size, so that whatever h you started with, the second one would be just half of that. That makes the formula much simpler, and this is actually the one that we will use for homework problems and that you would be asked to compute. So if you took an initial step h1 and h2 is just half of that, then you can exploit that relationship in this formula, and you'll come up with the fact that your new approximation would be based on weighting what you did when you took half of the step by 2 to the p, subtract what you got when you applied the rule with step size h1, and then divide by 2 to the p minus 1. So again, what the little g, the g's here are just representing a formula, like a finite difference approximation or whatever. So Richardson extrapolation works in general, where you have a representation of the error and a process to generate your result with a step size. So this is all very generic, but we'll show you how this applies for the particular case of approximating derivatives. So let's do an example of REF, or Richardson extrapolation formula. By this particular example, suppose that we wanted to approximate the second derivative at 1 for this particular function. Now, clearly you know how to compute the derivative of e to the minus x, and then you could easily compute the second derivative, so actually we could check our answer. But let's just suppose that we wanted to approximate f double prime of 1. And so what this would mean is that, we would approximate our function e to the minus x using a step size of h. Let's suppose it's 0.64, and we would get a result using an order h squared method for central differencing, and we would get this value 0.38061. And then we would half that value for the step size and use 0.32. Get a slightly different answer. It's actually, you'll notice, a little bit smaller than what we got when we put in 0.64. So again, the difference here is looking at our formulas for our finite difference approximations using different values of h. First using 0.64 and getting a result, and then using 0.32. Okay. So again, if we just go back to the formulas, what I'm talking about is using one particular value for h, or in this case we're doing the second derivative, one particular value for h, and then using another one, which is actually going to be half the size of it. Okay. So that's just what this g is. This process G is referring to. And of course, the truncation error, the central difference approximation, we already know is over order of h squared. So the leading term here, or the smallest power of h, is going to be 2 in the error term. Okay. So if we approximate f prime of x using 0.64 and setting p equal to 2, because we know that's the order of accuracy of our approximation method with central differencing, we would get this value. If we would apply REF, where we took in the result we got when we used 0.64, then the result we got when we used 0.32, we'll weight the second one with the smaller step a little bit higher, subtract the result we had before, normalize by this, and that is the new approximation. So again, if we go back, when you just do central differencing with 0.64, you got 0.38 something. When you halved the step, you got 0.37. And then now with Richardson extrapolation, we're dropping it even a little bit lower. It becomes 0.367843. You can show, though, because of the subtraction, this G of 3.2, when you're subtracting two different you're using the same finite difference approximations. Remember, this one, both of them are order of h squared accuracy, so the leading term involving h on each of those approximations is order h squared. The fact that you subtract them removes that term, and it goes to the next highest power of h, which will be h to the fourth. So you can show that by doing Richardson extrapolation, you will actually produce a result of order h to the fourth. Okay? The O of h squared term is eliminated. So we can ask the question, well, how well was the approximation improved by REF? If we go to the next slide, again, this is just the result that we did with REF, just for comparison purposes, because we would know analytically how to compute the derivative of e to the minus x, and then therefore the derivative of it, which would be the second derivative. That's what the exact value should be. This was, again, the result we had with 0.64. Then we halved that value to get this result. But you can see clearly that either using the independently using those finite difference approximations, was not going to get you 2 decimal digits of accuracy here, where at least you can see we've gotten 4 digits of accuracy lining up with RE. Again, O of h to the 4th accuracy in this case. So clearly, Richardson extrapolation has paid off to improve. I mean, it might be in some applications just knowing it's 0.3 something might be good enough. But if the scientist or the developer you're working with suggests that it's not good enough, then you would know, okay, well, let me try to do some Richardson extrapolation with 2 different processes using one particular step size h for my formula and then halving it, and then see if the extrapolation produces a better result. So let's do an example out of the textbook. This is example 5.2 on page 190 of the textbook, which is an illustration of REF, how to use the Richardson extrapolation formula. So suppose you had this data for x. You have functional evaluations at 0, 0.1, 0.2, 0.3, 0.4. Notice that's forward marching, especially if x was time. It's moving forward in time. F of x has the corresponding values in the table. You can see for each one of those. So the goal is to compute the derivative at 0. So we'd like to know what the derivative is doing at x equals 0. We want it as accurately as possible using REF with 2 forward different approximations of order h squared to the derivative. So again, we would use central finite differencing, first order finite differencing for that. We're approximating a 0, so we're trying to estimate, we're going to use this formula twice, and the question is what do we want to use for h? Now, you may be thinking, oh, you can use anything, right, and then have it. Well, you have to have the functional evaluations for f of x plus 2h and f of x plus h and f of x. So you've got to go back to your data. Again, x starts at 0, so clearly these steps are all of the same size. They're 0.1 steps, right? So it seems like a quick approach would be to just let h be 0.1, right? So for this first approximation of the derivative, you can see we're going to use this functional value for f of x, and then we're going to use f of x plus h, and then we're going to use f of x plus 2h. We're going to use that one for this formula. Then, for the extrapolation purposes, we take, actually, I was jumping my head. For the first one, we only need 3 points. So we're going to take this one right here. Then we're going to take this one right there. Okay, so I decided to clean this up. I need to make sure I use steps that are available from the data itself. So I need to take one step size and then be able to half it and still have data available. So what I can do is I can first choose h1 to be 0.2 and then the second one to be 0.1. Why do I say that? Well, I have to march forward, and I need to use 3 functional evaluations. So I can use these 3 to start with, right? And f of x would be here. F of x plus h would be this point right here, because they're going to start out with h being 0.2. And then the third value is 0.4. So I would use all 3 of those to get my first approximation using this step. Then the second time, my step is half as big, and I'll use 3 functional evaluations again. So in that case, I will not be able to use this value here as specified for the previous one, because now I'm taking a half step size. So the 3 in play are these particular ones. Let me go back to my pencil mark here. So when I go to 0.1, this is x plus h, and that's x plus 2h. So I think it's pretty intuitive. It's just how big are the steps. Start off with the big jumps, coarse, and then we go flying. So it's sort of coarse to fine grain in terms of how closer we are to the value of x where we're trying to approximate the derivative. We went kind of far out, all the way out to 0.4 for the first time, and the second time we're much closer in. Right? So if we do that, right, and so this reflects this first process of using, we're just using G as a process name, so G of H1 means use the central finite differencing, excuse me, it's not central, use the forward difference because we have to move forward from 0, we're not centered at all, and then use the smaller step size, which is halved, and then do our extrapolation using both of those, and we get 0.9927. Okay? And it turns out that's sort of h to the 4 accurate. So I think this is all we'll do in terms of an example of REF. It's pretty straightforward, and you can see that it's not very difficult to code this. You're just making a function call to your finite difference approximation method or function and just doing 2 calls to it and then taking this simple difference with some weighting of terms, and you will get a new approximation which hopefully will be more accurate, at least in terms of the error terms will be much smaller, h to the 4th versus h squared, which we really originally had with our central differencing formulas moving forward from the point x that we're interested in taking the derivatives at.